Time travel has long captured our imagination, blending the mysteries of geometry, physics, and the very nature of fate. But what if time travel could be more than just science fiction? Recent research suggests that closed time-like curves, or CTCs, might allow journeys to the past without paradoxes. To truly understand how paradox-free time loops could exist, we need to explore the deep mathematics behind them. This journey will take us through general relativity, information theory, and the surprising limits imposed by thermodynamics. Let's embark on a logical exploration of how mathematics might make time travel possible without breaking the universe. The heart of paradox-free time travel are closed time-like curves, or CTCs. These are special paths in spacetime that loop back to their starting point, allowing an observer to return to their own past without ever exceeding the speed of light. In the language of general relativity, a CTC is a smooth curve whose tangent vector always remains time-like. This means that mathematically, time travel is not forbidden by the equations of physics. But how do these curves actually arise, and what keeps them from causing logical contradictions? One of the earliest and most famous solutions to Einstein's equations that allows CTCs is Gödel's rotating universe. In this model, the entire universe rotates, and the geometry of spacetime is such that light cones tilt, making closed loops through time possible. Gödel's universe is mathematically consistent, but it comes with a catch. Causality is violated everywhere. This means that in theory, anyone could travel to their own past. While this is a fascinating idea, it also highlights the challenges of making time travel compatible with our understanding of cause and effect. Another intriguing solution comes from Frank Tipler, who proposed that a sufficiently long, rapidly spinning cylinder could create CTCs by dragging spacetime around it. In this scenario, the light cones near the cylinder tilt so much that world lines wrap around in time. However, Tipler's original solution required an infinite cylinder, and later work showed that a finite version would need negative energy, something not found in nature. This aligns with the chronology protection conjecture, which suggests that the universe has built-in safeguards against large-scale time travel. Closed time-like curves naturally raise the question of paradoxes. What happens if you change the past? Novikov's self-consistency principle provides an answer. It states that events along a CTC must be globally consistent. Paradoxical outcomes have zero probability. Recent work by Tobar and Costa formalizes this using quantum information theory. They show that if the dynamics along the CTC admit a fixed point, the system can evolve in a way that is always consistent, no matter how complex the loop becomes. This means that, mathematically, paradoxes can be avoided. The quantum version of time travel, a CTC, is modeled as a sequence of regions, each performing a local unitary operation on a quantum system. The key is the fixed point condition. The state entering the loop must be the same as the state exiting it. When certain operations commute, fixed points always exist, ensuring that even with free choice, the system remains paradox-free. This elegant mathematical structure shows how quantum mechanics and relativity can work together to allow time travel without logical contradictions. Time travel isn't just about geometry, it's also about information and energy. According to Landor's principle, erasing one bit of information at temperature T always dissipates a minimum amount of energy as heat. If time travelers bring knowledge from the future, that information must either be stored or erased, both of which increase entropy. This means that every loop through time comes with a thermodynamic price tag, linking the feasibility of time travel to the laws of heat and information. Jacob Bekenstein's bound sets a hard limit on how much information can be stored in a finite region of space. The more information you try to pack into a given volume, the more energy you need, and eventually you hit a ceiling. For time travelers, this means that each loop adds to the information load, and after enough loops, the system reaches its maximum capacity. Beyond this point, either the information must be erased, releasing heat, or the physical system breaks down. Arthur Eddington introduced the concept of the arrow of time, which points in the direction of increasing entropy. While the fundamental laws of physics are nearly time-symmetric, real-world systems overwhelmingly evolve toward higher disorder. Time travel that reduces entropy locally would have to be balanced by increases elsewhere, or else the second law of thermodynamics would be violated. This sets a fundamental limit on how time loops can operate in the real world. Cosmic strings, hypothetical defects from the early universe, have been proposed as another way to create CTCs. In theory, two rapidly moving cosmic strings could form a GOT time machine. However, even a single photon can destabilize this setup, causing the CTC to vanish. The omnipresence of cosmic microwave background photons in our universe makes such time machines inherently unstable, supporting the idea that nature protects causality through instability. String theory offers a broader perspective, suggesting that the Big Bang might not have been the true beginning of the universe. Instead, cycles of contraction and expansion could make time a global property, with local CTCs appearing as ripples. However, there's no evidence that such cycles allow for macroscopic time travel. The mathematics is intriguing, but the physical reality remains uncertain. Imagine a civilization facing extinction from an asteroid. using a time machine to repeatedly jump back and avoid disaster. Each new cohort of travelers brings extra information and energy into the past. The mathematics shows that the total information and energy load grows with each loop. Eventually, the system hits physical limits, the information capacity is saturated, and the energy required to erase or store data becomes astronomical. This self-limiting behavior is a natural consequence of the laws of physics. Einstein's field equations link the geometry of spacetime to its energy content. Each additional group of time travelers increases the stress, energy in the past, altering the curvature of spacetime itself. If too many loops occur, the accumulated energy can distort or even destroy the CTC, enforcing what's known as chronology protection. This feedback mechanism ensures that time travel cannot be used indefinitely without consequence. Combining information theory and general relativity, we can derive a stability condition for repeated time loops. The number of sustainable loops is limited by both the information storage capacity and the available energy for erasure. Once either threshold is crossed, the time machine becomes physically untenable. This mathematical result shows that perpetual time travel is impossible. After a finite number of loops, the system breaks down. Mathematics provides a powerful lens for understanding time travel. While general relativity allows for closed time-like curves and quantum theory offers self-consistency, the laws of thermodynamics and information theory impose strict limits. Every loop through time adds to the system's entropy and energy load, eventually exhausting its capacity. In the end, paradox-free time travel is possible in theory, but nature ensures it remains self-limiting. The dream of endless time loops is checked by the very fabric of reality.